Continuing on yesterday's session, we've started a new chapter. At some point, the plan is we'll go back and we'll finish the last sections of chapter 3. That was regression, where we first regressed our response variable, so the variable that we're hoping to predict, onto a single predictor variable. That is your simple linear regression, and extending that model to 2 or more predictor variables gives us a multiple linear regression. It's the same function in R for both simple and multiple linear regression. It's the one that we used in so many of our past sessions, LM, based on your response variable. Since it's regression, uppercase Y, the y-hats that we're estimating for the response variable, that's a numerical variable. It's quantitative. And the same applies to the predictor variables. So in linear regression, you're really working with numerical data. Moving to what we started in our last session together yesterday, classification models are when you are predicting something that isn't numerical. And there were 3 great examples over here. We can quickly go over them again, where your data is persons arriving at an emergency room. The predictor variables, so x1 to xp, for each of those observations is a set of symptoms for each patient, and you're then on the strength of that data, you're going to try and classify each individual under one of 3 medical conditions. Let's say you've ruled everything else out and you're down to 3 of them. Just to keep things simple, what kind of model would you design? It can't really be regression for a number of reasons. First and foremost, just because it's not numerical. It's not numerical. The medical condition might be a stroke, might be, I don't know, some kind of injury while boxing, and some other third condition. So that's the first example. Second example, online banking, and each observation is no longer a patient, but it is a transaction. And you're going to classify the transaction. This is now a binary response under fraudulent or not fraudulent. You're not looking at symptoms this time around as your predictor variables, but you're looking at the user's IP address, past transaction history, etc., etc. Third example, DNA sequence data for each patient. So it's in many ways similar to the first example, where each observation is a person. You're looking now at the genetic profile or a subset of each individual's genetic profile, rather than maybe more visible symptoms, as in or you know, macro symptoms, macro identifiers as an example 1, but you're drilling down in this example all the way to the DNA, and it doesn't really get more fundamental than that, does it? And in this example, let's have a look. You're trying to figure out which mutations are disease causing. Just as in the regression setting, in the classification setting, we have a set of training observations. It's these N observations, patients, persons, companies, transactions, phone calls, you name it, that we can use to build a classifier. We want our classifier to perform well, not only on the training data, but also on test observations that were not used to train the classifier. So this takes us back all the way to chapter 2, where we discussed that you would minimize not really the training mean squared error, but the test mean squared error. So data that hasn't been used to determine any parameters, to determine which predictor variables you're actually going to use, using some kind of hypothesis with maybe a T statistic or an F statistic. And we're going to look no longer at the advertising data, which had 3 predictor variables: the newspaper, the television, and the radio advertising budgets for, I think it was like 200 observations. Each one of them was a specific territory, country, city. Instead, we're looking at what is banking data, or what you would typically find at a lending institution, and it's a binary outcome. Will the individual default or not default? And as predictive variables, we're taking specifically 2, the annual income and monthly credit card balance. And we still have yesterday's code. Default is the data set. Could look at the summary, make this slightly wider. So this is our, let's clear everything again. Go back there. This is your summary. We actually have 4 variables. We may initially ignore this one. We're not going to ask our model to consider the impact. Remember, it's always a relationship, right? The impact of the borrower being a student or not a student on the likelihood of default. We mentioned it's this data set is exhibiting a 3% default rate. We were just over 3%. We have roughly 300 of the 10,000, and you can see the 10,000 over here. These 10,000 individuals, 300 of them defaulted on their loan. The default and student, that's factor data, 2 levels each, yes, no, to default and to student. And then we have, think of it as a box plot, the quartiles and the mean for the balanced numerical data. So that's how large the loan is, or what's left of the loan on relating to a credit card. And I think it's probably annual income, isn't it? So you have minimum of 772 with the highest earner having their salary listed, at least in the bank's records, as just over 73K. Visually, this is what's going on. And I really do invite you to view this specific pane as a 3-dimensional graph, like this one. It's really the same concept. The only difference is that the The response variable isn't numerical like sales. You aren't going to have from a negative to whichever positive value this is. Instead, since it's binary, default or not default, we are using one of two colors for each observation. Blue is no default, orange is default. These two charts over here, instead of taking a sort of like a three-dimensional thing, as in this one, blue depending on the income and the balance. Now we're just looking at those individuals who defaulted. That would be the orange, excuse me, those individuals who defaulted. What was their, for instance, median balance? And you can see it's significantly higher. The balance is what is yet owed on a specific card than the median balance for the observations that did not default. Whereas income, they are considerably closer. And the first question is, what is the statistical significance? We're going that step further than just intuition, but we would like to define something rigorously, usually using some kind of hypothesis testing to say with a 95% confidence, for instance, we can say that income is a driver for the probability of default. The same thing with balance or whichever predictor variable you're working. If you missed yesterday's session, I do encourage you to go over 4.2, where we're asking why not linear regression? And it really gives two major reasons. Instead, we're going to start with logistic regression. There is a bit of repetition from yesterday. We can do a lot worse than repeat the last few minutes from our previous session. Consider again the default dataset, where the response default falls into one of two categories, yes or no. Rather than modeling this response Y directly, so rather than the model giving you a yes or a no as a first and final step, instead we have this multi-step process where logistic regression actually gives you what we're going to interpret as the probability that Y belongs. So it is numerical, isn't it? And it's going to be from, we would like it to be from 0 to 1. Now, using linear, it's the same data set. We have, think of it as simple linear regression, where we're regressing. Now granted, this chapter is all about classification models, not regression models. But for the time being, think of this blue line as a simple linear regression model. Go back to secondary school when maybe you did your first lab report on Hooke's law, and you're only looking at the extension regressed on the mass of whichever weight is pulling the spring or the material. But it's binary, so the only Y values that we have are 1, meaning defaulted. This is our training data set. We know that all these observations, those are the ones that defaulted for a range of balance values, and then these are the ones who didn't default. So really, this chart on the left is basically this chart over here. Very, very similar, just maybe we've just rotated things slightly. This is one box plot, or you can think of it as one box plot. The second one being over here. What it doesn't really give you is the data points are so close to each other, you kind of lose in such a diagram. You can't really tell the density. How many data points are there over here versus how many there are over here? They're so close to each other, it's hard to make out. It's actually impossible to make out. There are so many of them that they just blur into each other. So that's one thing. That's one thing you can't tell over here. Whereas over here you can tell there are only a very few individuals that did the fault. So probability 1 for low balance values. Now, we're seeing one of the issues of linear regression and why we cannot use linear regression, or why it wouldn't make much sense to use linear regression. The fitted model, which is this blue line, is giving you, for values roughly less than 500, negative probabilities. And if you had to keep on moving further to the right, eventually you'd also get probabilities greater than 1. So instead, we're going to read this. Instead, what we have is what I'm pronouncing as logistic. I hope it's not logistic. Logistic regression. I would imagine log just being log, right? A logarithmic function. We know what logarithmic functions are, right? So think of your exponential functions. So for example, y is equal to 5 to the x. So 1 would give you an input of 0 would give you 1, an input of 1 would give you 5, an input of 2 would give you 25, an input of 3 would give you 1 to 5. Now, if you had to invert that, you invert an exponential relationship using a logarithmic relationship, and that would look like they don't intersect. And that would be log base 5 of x. So 5 to the power of and log base 5 are each other's inverse, and probably the logarithmic function that is most used is ln, where you're inverting e to the power of x. That's Euler's constant, many special properties for this relationship. Maybe first and foremost that it is its own derivative. Derivative of e to the x is e to the x. For the default data, the logistic regression models the probability of default. For example, the probability of default given a specific balance can be written as probability default equals yes given the balance. So what this blue model is doing is just telling you, given that the balance is 200, what is the probability that that person defaults? And that's 60%, for instance. Given the balance of 2500, then the model tells you, in that case, the probability of default is over 90% in this case. And it's non-linear, right? So moving 1 unit in balance, it depends on the balance that you're starting with. So at 500, increasing the balance to 501 doesn't really move the probability of default, but the curve is most sensitive where it is steepest to changes, to differences between one person's balance and another person's balance. And again, all this for the time being is we're just looking at a single variable. Very quickly, we'll try and see how to incorporate not just balance, but we mentioned annual income, for instance. If that person is a student, which is a qualitative predictor variable, and we're going to see all these things very soon. The values of probability default equals yes, given the balance, which we are going to abbreviate to P balance, will range between 0 and 1. Then, for any given, this is the next step. This is the next step where we're actually going to say default equals yes or default equals no. So far, we're only speaking of probabilities. Then, for a given value of balance, a prediction can be made for default. And now there's a bit of a judgment call. For example, one might predict default equals yes for any individual for whom the logistic regression is giving you a probability of that person's balance is greater than 0.5. Alternatively, if a company wishes to be conservative in predicting individuals who are at risk for default, then they may choose to use a lower threshold, such as P balance is greater than 0.1. And there's always a bit of a trade-off over here. If you're going to be too conservative, conservative isn't maybe prudent or pessimistic. Conservative is a bit of a loaded term. If you're going to be too pessimistic, you end up possibly not lending anyone anything, right? Or asking for demanding higher interest payments that you'll just lose a lot of business to your competitors. How should we model the relationship between P of X? That's just notation. So please, whenever we say P, lowercase p of X, it simply means the probability that the individual defaults, y equals 1, we have 0 or 1. 0 does not default, 1 defaults, given a value of X. Given that value of X. Just keep on thinking of X as the balance. So what we're asking is, what is the probability that an individual with 2,000 balance defaults? What is the probability that an individual with 500 balance defaults? So those two probabilities, we're going to denote them as, or by, P of 2,000 and P of 200. And we want a relationship. This is the whole thing about statistical learning. You want a relationship between the probability of default given X and X. And we're expecting the larger the loan, the higher the probability of default. For convenience, we are using the generic 0-1 coding for the response, and that one just referring to this one. In section 4.2, we spoke of using a linear regression model to represent these probabilities. So you would say, if you like, if I simply change this to y, this would now be chapter 3, right? If this was y, this is exactly what we did in linear regression. X is a numerical variable, balance, but y would also be numerical. Instead, since we're working with qualitative response variables, so defaults, does not default, wins the World Cup, does not win the World Cup, arrives late, does not arrive late. To make it numerical, and we like numbers, we would like to add a number to another number and gives us a number, we will speak of the probability of default given X. So this is not the probability of X. This is not the probability that I don't know, you pick a random client of this bank and they have a balance of X euros. No, this is the probability of default given X. So kind of need to watch out for this notation because I mean, I'll be honest. If I didn't repeat this just now, I wouldn't be surprised if I would have done the next half hour thinking that this is probability of X. No. This is the probability of default given X. It's kind of a pity they're writing it like this. Anyway, we're just going to have to live with it. The probability of default given X is equal to, in some relationship with X in the expression describing the relationship. If we use this approach to predict default equals yes, using balance, then we obtain the model shown in the left-hand panel. This is what we discussed earlier. Here we see the problem with this approach. For balances close to 0, we're predicting a negative probability, and for very large balances, probability will exceed 1. These predictions are certainly not sensible, since, of course, the true probability of default, regardless of credit card balance, should really fall between 0 and 1. This
Stuart?
Yes, please.
When you say default, what do you mean exactly?
Oh, yeah. So sorry about that. Default, even if we look at, I can probably do a lot worse than the actual description in the package. It's always a really great idea. If you look the package up, it typically, and you click on the link, it first of all, clicking this probably takes me to I don't know what. We'll look at it another time. You have the list of functions and you have the list of data sets. This is a package which appears to only contain data sets. And if we click on default, we have the documentation describes each variable. It also tells you from where. Oh, okay. So it's actually just simulated data. It's synthetic data. It's not actually collected anywhere. So the income is the income of the customer. The balance, I mean, balance could mean so many different things. Over here, it is the average balance that the customer has remaining on their credit card after making their monthly payment. Student is, well, customer is a student or isn't a student, and default is a factor with levels no and yes, indicating whether the customer defaulted on their debt. So if I owe you, if you lend me 50 euros and with, I don't know, a 1% per annum interest, I will be considered, I will have been considered to have defaulted on the debt that I owe you if I don't pay it off. Possibly if I fall behind in payments. It kind of depends on the precise definition that you're using of default, but just the simple way, and you know, if anyone wants to chip in over here, the default is not paying your debts. For example, filing for bankruptcy, fleeing the country and never being seen again. That's default. And anyone that's, especially a bank's business model is lending money. Very often it's not its own money. It's kind of borrowing at one interest rate and lending at you would imagine a higher interest rate, and that margin is where the profit is to be made. But there are risks, and the risk is that you lend money if you are a bank to a company, an individual that doesn't make good on their obligations. And finance is all about obligations. If it's an insurance contract, you have the policyholder. Think of an individual who's just taken out a motor insurance policy, transferring the risk, so the risk of knocking someone down if it's third-party motor insurance liability, the risk of the car being stolen, so that would be you would include as one of the risks being covered, theft, etc., etc. There is a transfer of risk from the policyholder to the insurance company. So that would be an insurance contract. Whereas if it's a loan, if you buy a bond, for example, if you buy government bonds, those are loans. The specific government, and it is borrowing money by issuing bonds. Insurance companies, very often, insurance companies are major players in the bond market for a number of reasons. And you could have some very famous cases. Soviet Union, for example, right after well, at its very beginning, had defaulted on its foreign debt. Russia in the 90s as well, under Yeltsin, had defaulted in one way or another on its debt. And the bank is asking, when you present yourself to your, I don't know, it's a loan application. Banks will have questionnaires, and depending on the answers to those questionnaires, assuming that they have been answered in good faith, and they do actually give a proper an accurate and faithful description of the borrower's characteristics, the bank will decide to issue the loan, to lend the money, or the bank will say no. It's one of the main drivers of the subprime mortgage crisis, which is probably in our lifetime. Yes, that definitely beats anything else, I think. We're talking 2008 roughly, where the subprime was that banks were lending to individuals that historically had been considered risky borrowers, but what there was a sort of like I don't want to get into, but there's something Freddie Mac, Freddie May, and something else, and the government was underwriting. The U.S. federal government was underwriting, so it's kind of like insuring. Is one way of thinking of it. It could be student loans as well. That's another type of loans, very topical right now in the US, because there's a lot of talk of how student loans have increased these past 15 years. Student loan forgiveness, which is something that's, I think, passed in etc., etc. But a default, just to keep things simple, a default is when a person, just think of it, they don't pay back the full amount of the loan plus the interest due on that loan, and the interest is there. The interest is there to reflect the risk that the bank is, or whichever lending institution is taking on when lending the money. So that's a default, and we're trying to relate it to the balance. So that the balance is it's a measure of the size of the credit card debt in the specific data set. So for balances close to zero, yeah, we get a probability that and that. So this problem is not unique to the credit default data. Anytime a straight line is fit to a binary response that is coded as 0, 1, in principle, we can always predict probability responses 1 given x is less than 0 for some values of x, and probability of default given x is greater than 1 for others. Just because a straight line, if you remember your A-level terminology, there's the concept of surjectivity. A straight line, it's not like a quadratic where it sort of has a minimum and it can never give you, at least if it's a U-shaped parabola, it can never give you an output lower than that minimum. A line can give you any real number as an output from negative infinity to infinity. Infinity is not a number, but that's how we typically describe the real line. So we're going to do away with linear regression, and this is where we're going to discuss logistic regression. To avoid this problem, we must model probability default given x using a function that gives outputs between 0 and 1. So I can think of a very, just to avoid, just to, well, not avoid, but just to give you an idea, you could use maybe tangent to get from 0 to 1. You could easily, you might need to invert it. So what if I do arctan? Yeah, see, look, arctan, and you have your asymptotes. What are your asymptotes? Your asymptotes are, I think, pi on 2, y equals pi on 2, and y equals negative pi on 2. So now I just want to scale everything that I'm only working within the output range, the output interval. Yeah, it will be a range from 0 to 1. How do we do that? It has a width of pi, I think, right? So do I just divide by pi translated by 1/2? Look, what we have now over here is this is a function that it's not logistic regression. It's not using logarithms. Think of it as maybe sort of like a trigonometric regression. It's using the inverse of tan. Remember, tan is just the ratio of sines to cosine. And this is guaranteed to give me an output from 0 to 1. Can never give me less than 0, can never give me more than 0. It's just an example that occurred to me while reading this right now. But we're not going to use tangent. We're not going to use tangent. Instead, and again, just to take it back to tangent, but you might want it for some kind of parameter. You might want it. So look, this is sort of like a negative relationship. The higher your input, the lower the probability. And this is the other way around. And think of this A. You find a parameter that best, whatever we mean by best. So for example, in least squares regression, best is the parameters that minimize the residual sum of squares, the RSS. And these are all different models. Every time I pick an A, that's a different model. And I could pick a B, right, as well, I would imagine. If I say B equals, look, so like this, and for every A and B, actually just set these as running. For every A and B, we have different models over here. And then you'd see how you determine the A hat and the B hat that best follow the data and that hopefully minimize the not just the training mean square error, but the test mean square error. And you know, we could have a look at this right now. We could do this in Desmos as well. We'll just read it and then double back and return to Desmos. Many functions meet this description. I'm just showing you one using tangent inverse, arctan. In logistic regression, we use the logistic function, and that is the probability of default. Please, it doesn't need to be default, right? It could be the probability of arriving late, the probability of divorcing, the probability, what is something that isn't binary? I don't know, the probability of picking a certain course at university, or the probability of continuing your studies after your bachelor's degree. I mean, if you had to ask the university, they would have all of that data. If it's a university that's been operating for enough years with enough students, they have a very, very good idea of who is likely to, for example, not just stop at a bachelor's degree, but do a master's degree. For example, I would imagine one of the major predictors is family background in terms of affluence. If you can afford to maybe do another year living with your parents, not necessarily working a full-time job, and extending your studies by a further year, yeah, you're more likely to do that, right? To fit the model 4.2, and now we're speaking of fitting. So that means determining beta naught and beta 1. We no longer have sum of least squares as a linear regression. Instead, we're going to use a method, and this is such a powerful method. There's going to be quite a bit of mathematics over here, and we get to use differentiation, which, yeah, big fans of differentiation, called maximum likelihood. So we're going to choose, in linear regression, you choose the parameters that minimize the residual sum of squares. Over here, we're going to pick the parameters that maximize what we refer to as the likelihood. And we'll see exactly what we mean by this. Apparently in the next section. So let's have a look. Let's go back over here and just start a new page. So the function is p of x is equal to, I'm not entirely sure. Is it a plus, yeah, this must have this bit of an annoying feature. Is it, yeah, that looks correct. Let me just have a look at the book. Uh-huh. Look, or shall we just keep it? No, this is your logistic regression. And for example, you can, yeah, like this, and you translate it like this. So you have these two parameters. We're going to determine them using maximum likelihood. You see it abbreviated as MLE, maximum likelihood estimate. or estimate. I can't remember quite which. And you'll get an A and you get a B, and these give you a different fit to the model. Again, statistical learning, the model, you're training it on whichever data, you're feeding it, and then from that point onwards, it's making predictions. However, there's a bit of a judgment over here. We have a certain level of discretion in classification problems that we will say, okay, if the probability is greater than, we'll say default yes, depending on we get to choose the cutoff probability. We're going to see all this very soon. So the right-hand panel is what we were looking at earlier, and in Desmos as well, illustrates the fit of the logistic regression model to the default data. Notice that for low balances, we now predict the probability of default as close to, but never below 0. Likewise, for high balances, we predict a default probability close to, but never above 1. The logistic function will always produce an S-shaped curve of this form, and so regardless of the value of x, we will obtain a sensible prediction. We also see that the logistic model is better able to capture the range of probabilities than is the linear regression model in the left-hand plot. The average fitted probability in both cases, average fitted probability in both cases, so linear regression and logistic regression, is 0.0333 averaged over the training data, which is the same as the overall proportion of defaulters in the data set. I don't think this is that important, but the 0.033 is just referring to the number of individuals that actually defaulted on their loan. So I think on average, both models give you the same thing, so on average, but the logistic is better for individual predictions. Like you just give it a single single potential customer or borrower. Now, after a bit of manipulation, so we're taking this and we're simply cross multiplying. So pink times pink, then we, etc., etc., etc. And what you can do is you can make this subject of the formula, and it is equal to probability default given x divided by, well, if it's 1 minus, this would be the probability does not default. So what we have over here is probability default. That's over probability does not default. And it's equal to this expression over here. Now, the ratio of probability does against probability does not is called the odds. And you read this as a ratio. So, for example, I don't know, if we go back over here and we see odds in horse racing, for example. So odds in horse racing represent the chance a horse can be given of winning a particular race. So a horse that is 2 to 1 is thought to have more chance of winning than a horse that is 8 to 1. So what are we saying? 2 to 1, would that be a probability of 66%? Because it's yeah, I think so, right? It would be sort of like 66% winning, 33% not winning. And isn't that 2 on 1? 8 on 1, 8 on 1. That means, well, the number's a bit more awkward to work with over here, but would I multiply? I wish it was, yeah, you could multiply by 11, top and bottom, and you get 88% and 11%, which isn't quite 100%, but close enough. Maybe I needed to multiply by whatever. So 8 to 1, 8 to 1. Wait a minute. No, that can't be right. That can't be right, because it said a horse that is 2 to 1 is thought to have more chance than a horse that is 8 to 1. Ah, okay, so I've clearly got this wrong. I don't know if anyone has more experience.
It seems to be explained in the middle of the screen.
Okay,
What the odds mean
here,
was betting.
this one.
Yeah.
So let's see. Let's see. So 7 to 5, you'll get 7 units for every 5 that you wager. Let's see what the book has to say. Let's not, and it's getting quite late in any case. But
I think what it means is that if you wager 1, for example, you get 2, right?
yes.
So if you're willing to bet 1 on someone who is likely to lose, you get 8.
Because there are
So the 8.1 is a riskier bet, basically. So you get a higher reward.
Definitely. But then why aren't we saying probability win? I don't know, maybe it's slightly different from what we're doing over here. Let's see. So look, we have a probability. So these are the odds, and they can take any value between 0 and infinity. Okay. Values of odds close to 0 and infinity indicate very low and very high probabilities of default. Very low. For example, on average, so if the odds are 1 to 4, that means that 1 in 5 people will default. Let's see why. I mean, it makes sense, right? I mean, the 5 is just 1 plus 4, but let's see how the book is doing it. So we have if you have the probability is 20%, which is this 20%, then you get 20 all over 80, and that's your 1:4. That's your 1:4. Likewise, an average, so if the odds are 9, that means 9 on 1. And that would mean that 9 out of every 10 people. Odds are traditionally used instead of probabilities in horse racing, since they relate more naturally to the correct betting strategy. Okay. I definitely don't feel I've developed. I think I can definitely improve on my own personal understanding of what odds are, but please just think of it, for the time being at least, the probability of default is to the probability of no default. The higher this ratio is, so for example, 9 is higher than 1/4, it means then just the more likely it is that given balance X, that there is a default. Now we're applying logs to both sides, and this book uses LOG. LOG means base E. It's quite common in statistics. Probably most of us are used to writing ln or log E, and whatever your input is, ln of something, log E of something. Many statistics books, at least the ones I've used in the past, and this would seem to be no exception, just use log. Log to mean the natural log base E. Just going to go back over here just to get an idea of the time. Okay, so we'll try wrapping things up. We haven't actually done any new material next to yesterday's session. I still feel that we've covered a lot, and I think we all needed a bit of this. We're starting a new chapter after all. By taking the logarithm of both sides, we arrive at this. The left-hand side is called the log odds, or the logit. We see that the logistic regression model has a logit that is linear in X. 4.2, 4.2. So this, and it's what we've been using this whole time. It just means that the logit is linear in X. Meaning, if you had to plot this against this, the red against the red, it will be a linear relationship. That's all we're saying. Recall from chapter 3 that in a linear regression model, beta 1 gives the average change in Y associated with a 1 unit increase in X, whatever the value of X is, right? Since it's linear, the gradient is the same everywhere. So wherever you are on the line, it's the same slope. In contrast, in a logistic regression model, increasing X by 1 unit, changes the log odds by beta 1. So we still have a similar idea where whatever your input is, a balance of 500, a balance of 2000, if you change it by 1 unit, even in logistic regression, there is something that always changes by the same amount, but it is the log odds, not the odds themselves, the log odds. So the log odds would increase by beta 1. However, because the relationship between probability of default given X and X in 4.2 is not a straight line, beta 1 does not correspond to the change in the probability of default associated with a 1 unit increase in X. The amount that P of X changes due to a 1 unit change in X will depend on the current value of X. What we're saying is the model is sensitive in different ways to different inputs. So over here, you basically have a gradient of 0, positive, very positive, less so positive, and it depends on the input that you are actually working with. What we'll do tomorrow is we'll start discussing the mathematics of likelihood and maximizing the likelihood or the log likelihood. If you're not familiar with this notation, it hopefully reminds you of when we would have sigma, uppercase sigma, for summation. But instead, this is Greek letter P for product this time around. So we will be multiplying these probabilities. The probability of xi and 1 minus the probability of xi. But we'll do this in our next session.